So, we saw that if you add this spin orbit interaction L dot S term on harmonic oscillator single particle nuclear potential, you reproduce all the magic numbers. So far as these shell closures are concerned, magic number are concerned, it does not matter whether you take infinite square well potential or this harmonic oscillator potential or a finite square well potential, with everything you can get those magic numbers, but the values of energy, the separation between different energy levels for example, or sometimes the order of energy levels inside a subshell, that is a function of what kind of potential you choose. So, for any realistic calculations, people choose more realistic potentials. So, as compared to infinite square well potential or harmonic oscillator potential, finite potential, finite square well potential is more realistic, because as we discussed earlier, you can take out a neutron or a proton from a nucleus, whereas these infinite potentials, they do not allow you to do that. Then the sharp change in potential, as in finite square well potential, suddenly it becomes 0, right, the shape of that square well potential, suddenly it becomes 0 after some r equal to capital R. So, that is also a little bit unrealistic. So, people add on it some kind of rounding off at the edge, finite square well potential, but then some kind of rounding at the edge to make it more realistic. The one which is which suits all these discussions is Wood's action potential, and Wood's action potential, where the shape is something of this type. So, no sharp edges and no infinite potentials. So, V as a function of R, this Wood's action potential, that is taken most in many of the calculations as the basic single particle nuclear potential, and on this one adds L dot S term with appropriate strength to get all those energy levels. So, I will show you on the screen how this varies, how this differs from harmonic oscillator energy levels. If you use those harmonic oscillator energy levels and then apply L dot S on it, you do get some energy levels, and if you use this type of Wood section, normally this is around 50 MeV depth, and this R depends on the size of the nucleus, and this how it tails off, that is A, right. So, how these energy levels compare with the harmonic oscillator energy levels?
Why it is called Wood section?
Those are persons, those are scientists who had come out with this kind of potential. So, the name is there to give them credit, that okay, these are the persons who had Lennard Jones potentials. So, they were scientists who came up with this potential, that look, use this potential and you get the desired results. I will just go to the screen and you see how these energy levels differ from, and how do they compare from this right. Okay. So, these are the harmonic oscillator potentials. With the harmonic oscillator potential, these are the energy levels. This you remember?
Yes, sir.
1s, then 1p, then 1d, 2s together, degenerate, 1f, 2p together, 1g, 2d, 3s together, right, that you can write easily. Okay. This is how the Wood section potential, Wood section potential will look like. Now, compare 1s, I have drawn at the same height, 1p has come down, right. Then 1d and 2s both have come down. This is the general feature. From infinite potential, if you are coming to finite potential, normally your energy levels will come down in that case. So, 1d and 2s are coming down by different amounts, and therefore, the degeneracy is lifted. Okay. Similarly, 1f and 2p, they have come down by different amounts. 1f has come down more, 2p has come down less, and that degeneracy is lifted, and 1g from that upper state has come down by quite some large amount. So, that it is at that almost at the same level where the original 1f 2p was there. Similarly, that 2d 3s they have come down, and the last line that you are seeing at the top is coming from 1h. Next level was 1h, and then this 2f 3p, those things were there. So, that 1h has come down significantly and it is there. Now, if you add this spin orbit potential on this these levels, see what happens. So, you have this Woods action with L dot S term. So, 1s becomes 1s half. What is that half? J value. L and S they have combined and they have given us J. So, S state L is equal to 0 and spin is half. So, J is half. So, it is 1s half, and this 1p has split in two parts, p j equal to 3 by 2, that we called p 3 half, that has come down, and 1 p half has gone up. So, this 1 p is split, degeneracy lifted. Next one, 2s will not change, because if in S state that L dot S term is 0. So, that does not change, that does not split. 1d will split in two parts, d 5 by 2 coming down and d 3 by 2 going up. Then here is 1f and 2p. So, 1f has split in two parts, the lowest one is f 7 by 2 and f 5 by 2 has gone up. Then 2p also splits into part, 3 by 2 and half. P 3 by 2 is coming between the two f states. Okay. So, 1f has split in two parts, one f 7 by 2 and one f 5 by 2, 5 by 2 going up, 7 by 2 coming down. 2p has also split in two parts, p 3 half and p half, and the structure that we have drawn is that 2p 3 half is coming between f 7 half and f 5 by 2. Right. Then you have 1g. So, 1g will split, and 1g splits in two parts, g 9 by 2, g 7 by 2, and 2d on top of that you have 2d, that will also split, 3s will not split. So, 2d goes like this, and then you have this 3s coming, okay, and then you have this 1h coming from the top, right, 1h 11 by 2 coming from the top. These are the energy levels if you use this Woods section potential, and the magic numbers are same, shell closures are at the same place. S half will have 2 occupancies, 2 neutrons or 2 protons can go there. So, 2, similarly that p 3 half and p half that combined will give you 6. So, the next shell closure is 8, then 20. 1 f 7 by 2 is stand alone. So, 8 nucleons can go there, 8 nucleons of the same type, 8 neutrons or 8 protons can go there. So, that shell closes 28, and after that the shell will close at that g 9 by 2, that will be 50, and at h 11 by 2 that will be 82, and similarly you can go up, you will get that to 126. Okay. Now, I will like you to practice writing these energy levels at least up to say 50 nucleons, that magic number 50. Okay. So, we will just try to do that on board, you can do on your notebook, so that whenever need arises you can write this order of energy levels, these sub levels quickly. Okay. So, let us do this manually on the board. So, you can start with the same in the same fashion, 1s and then 1p like harmonic oscillator, and next one is
1D.
1D and 2s. So, 1D will come down and 2s will be slightly up, they are split. Right. Then 1D and 2s, next will be
1F.
1f, so 1f will be somewhere 1f and 2p, 2p will be slightly up, so 2p somewhere here. So, this much you can write quickly. If it is harmonic oscillator, it is 1s, 1p and then 1d and 2s together. So, you split them little bit and then next one will be 2p and 1f. So, you split them. Then putting that L dot S term, this p, what will you do with this p? You will put it in two parts.
P half,
P3 by 2 down, P half up, right. So, this P goes here, then this D, you can, this shell is closes at 2 and this is 6. So, this closes at 8, next closes at 20, 2 and 8, 10. So, 10 more. With this D, what will happen? D3 by 2 will come down, D5 by 2, right. D5 by 2 will come down and then D3 by 2 will go up and this 2s will remain there. So, this 2s will remain there. If you wish, you can also write that n. So, this part, up to this part you can do that easily. And how many, what is the number of neutrons or protons that can be accommodated? 6 plus 2 8, 8 plus 4 12. So, 8 plus 12 20. Then f7 by 2 will come down and that will be alone 1f7 by 2. So, that is next cell closure and f by 2 will go up. So, f by 2, f5 by 2 go up and then this 2p, this 2p 3 by 2 and 5 by 2 and how is that written? How is that written? F comes between the 2p levels. Okay. So, this 2p, let me write it slightly lower. So, that this 2p when it splits, one level goes here and another level goes here. This is 2p, this is 2p 1 by 2 and this is 2p 3 by 2 and this one is 1f 5 by 2 in between. How many? 4 plus 6 10 and plus 2 12. Okay. And did I okay. So, this is how much? 12 and 10 will come from 1g. Next one is 1f 2p, one is 1g, 1g will be there, then 2d will be there and 3s will be there. So, this 1g will give you, 1g will come down and join here, 1g 9 by 2. So, that makes it 12 plus 10 22 and 28 plus 20 is 50. So, you do not have to cram these levels that first it is as half, then P3 half, then P half and then D 5 by 2, then it's almost impossible to cram all those things, to remember all that order, but you can construct them. Okay. If you remember the basics of how it is splitting and how it is ordering, from that basic knowledge you can construct it in how much time you will take from a clean slate. If you have to write all these things, how much time will you take? Guess how much time you will, suppose I rub everything and ask you to write the levels starting from scratch, how much time will you take?
5 minutes.
5 minutes, 2 minutes, maximum 2 minutes. What do you have to do? You have to first imagine your harmonic oscillator potential 1s, 1p, 1d, 2s, 1f, 2p, and then 1g and 2d and 3s harmonic. That should take you some 30 seconds. Okay. Then write them, separate them little bit. In harmonic potential you would have written these things at one level, these two at one level, these three at one level, separate little bit. And remember, higher L value or lower N value, that will come down. So separate that. So writing this and this 1g, at least 1g should take about 30 seconds, and then you have to split. 1s will remain as such, this will 3 by 2 coming down, 1 by 2 going up, d 5 by 2 coming down, 3 by 2 going up, and this s is in between, right. F comes down, and this is you remember that this closes at 2, next magic number 8, next is 20, next is 28. So this 8 will be alone, and its corresponding 5 by 2 will go up, and this p will split in two parts, and this f is sandwiched between p half and p 3 half, and 1g comes from here, and you reach this 50 magic number. So now tell me how much time you will take. 2 minutes or 1 minute? 1 minute. Yes, it should be able to do it in 1 minute. Okay. Whenever need arises, you can you should be able to write it in 1 minute. Okay. All right. Good. Now there are certain things about this ordering. One is this nuclear potential depends little bit on the size of the nucleus. Okay. Because more is the bigger is the size, this potential that you have written will be wider. So the basic features remains the same, but the values of energy will change. The values of energy will change, and therefore the separation between different energy levels, that separation will also change. That will depend on how big is the nucleus. And if the separation changes, sometimes it may also happen that two adjacent levels cross over. It may happen. Suppose this separation is changing as A is increasing and the separation is decreasing. So at a certain extent it can cross over, it can interchange. That happens first here. This 2s half and this 2d3 half. Here we have written 2s half between the two d levels. Okay, this d level is splitting in one part here, another part here, 2s is remaining here. Now around A equal to 50 or so, around capital A equal to 50 or so, this switches. So for this is for lower values, A less than 50. Okay. If A is larger, then this section, all these things, the order will remain the same. The separations can change, but order will remain the same, but this portion will become d 5 by 2 and then d 3 by 2, 1d, 1d, and then 2s half here. So this order can change. Similarly here this order can change, this order can change somewhere A greater than 60, 70 and so on. So just keep this in mind, it is not a strict ordering, but if you normally shell model is used is quite successful for lighter nuclei, and then in the middle heavy range also there are sections. So for lower and lighter nuclei this is very good. And if you are more than 50, more than 60, more than 100, then at some places you may get some crossovers, but the group will remain as such. It will not, no level will leave its own group and come join another group. So the magic numbers will remain the same. So that is one. Second thing is average separation between the energy levels, that decreases as this nucleon number mass number A increases. Right. It comes from experiment essentially, that last filled energy level, you can call it nuclear Fermi level, last fill energy levels, that is that does not vary much. Light nuclei, heavy nuclei, middleweight nuclei, that does not vary much, varies within say 5 to 10 MeVs or so. Similarly, that depth of the potential, that also remains almost the same. So, this total occupied energy difference, the bottom and the top, that is of the same order for all nuclei. And then if A is large, then those many energy levels should be there. If A is small, then less number of energy levels are there. I am only talking of occupied energy levels. So, the highest occupied energy levels, if that remains almost at the similar place, and the lowest energy level that remains roughly at the same place, and then you are pushing 10 nucleons. So, you should have roughly 5 levels each one, or yeah, in fact 10 nucleons means protons and neutrons. So, one energy level will take 4, 2 protons and 2 neutrons. So, you will have, but if you have say 200 nucleons, then all those 200 are to be commutated. So, you should have 50 levels in that same range. So, that average separation between the energy levels, that is you are seeing here, that is a function of capital A, and as capital A will increase, this whole thing will get squeezed. So, in the same height of the blackboard, you should be able to bring all those 126 and 180, all those things you should, it is all compressed. The separation, average separation between the energy levels decreases as capital A increases. That is why in semi empirical mass formula, when we were writing that asymmetry term n minus z whole square divided by capital A. So, that is because of this. The third thing is this potential, these energy levels or this potential itself is somewhat different for proton and neutron because of Coulombic interaction. If we are writing for neutron, it is a single particle potential. For all nucleons, we are saying that this is the potential and these are the energy levels. But then that single particle, if it is neutron, it is not experiencing any Coulomb interaction. Whereas, if it is proton, it is interacting with the rest of the nucleus through Coulomb potential also, Coulomb interaction also. Right. So, the potential is somewhat different for proton and for neutron. In lighter nuclei, it does not matter much. Right. Light nuclei, it does not matter much, and the levels are same, almost the same. On the but for middleweight or heavyweight, this Coulombic interaction may become significant as compared to this nuclear potential depth. Okay. You remember the formula for Coulomb potential? If you assume it to be a spherically charged system, spherically symmetric charge distribution, Z Z minus 1 E you can say, then the Coulomb potential can be written as, or Coulomb potential energy can be written as some Z E square 4 pi epsilon naught capital R is this, and then 3 by 2 minus 1 by 2 R by capital R square. Right? We had derived this when we were considering the radius of the nucleus, initial lectures, and how this electrostatic interaction between the nucleus and the electron changes the energy, and X-ray energy, K alpha energy, all those things we had discussed. So, we had derived this equation that time. This is class 11th. So, Coulombic potential is like this. So, for low Z, if the you have light nuclei, Z is low and it does not matter because this is quite high, but for middle and heavier nuclei it will matter. This is for R less than R, and R greater than R also you have electrostatic potential because it is a long range force, and that goes as 1 by R. If you have Z, E or Q charge in this sphere outside, the potential will just go as 1 by R. So, your potential, first thing, it is lifted up, it is positive, right, proton and the rest of the nucleus both are positive charge. So, it is positive. So, it will lift up at r equal to 0, small r equal to 0, it is 3 by 2 times of this. So, this much is added. At r equal to capital R, this is 3 by 2 minus half is 1. So, this into 1 lifted. So, at the center it is lifted more, here it is lifted less. So, overall it is lifted, and then you have this 1 by R type of fall. So, this is how the potential will modify. For neutron, potential is like this, for proton potential is like this. So, if I draw both side by side, suppose this is the potential for neutron, and then I can draw a similar thing here. This is 0 and this goes up, this was the original level and now this has been shifted up. It goes up and then it falls, 1 by R type. Okay. Now, the energy level, suppose it starts here. If these are the energy levels, correspondingly you will have energy levels here. But these energy levels are missing. For neutron, the energy levels will start here and here it will start here. So, that is one simple effect. Another effect, because of this lowering of this depth here, this spacing is little bit larger than this, and if the nucleons are to fill this these energy levels from bottom to keep the total energy of the nucleus minimum possible. So, neutrons, and if neutrons and protons are allowed to interchange beta decay. So, the energy will be filled up to some level, right. If that be the case, you will have more neutrons and less number of protons, because top the energy should be same. If we are filling higher levels, then it should change through beta decay and then fill that lower energy levels. If you have to keep the total energy of the nucleus minimum possible. Right. So, protons and neutrons both should fill up to almost the same level. Pauli exclusion principle has to be obeyed up to same. Otherwise, if you have much more things there, they can interchange between the neutrons can go into proton or proton can go into neutron, and these empty shells will be filled up. And if it is to be filled at the same level energy, same energy, then the number of energy levels appearing here is less, number of energy levels appearing here is more. That means, you will have more neutrons than protons, n greater than z. So, this is one way to understand why in heavier nuclei you have more neutrons than protons. For light nuclei, Coulomb interaction is not very effective, and therefore, the two potentials and two schemes of energy levels are almost the same. Right, and therefore, n is equal to z. To keep that energy minimum, n is equal to z. But once this Coulomb interaction becomes effective, then to keep that total energy minimum, you must have larger number of n neutrons than protons. So, these are some of the things which I wanted to talk about that. Now, coming to connecting this whole model, this whole scheme to the measurable properties, the first thing which the shell model can quite satisfactorily explain is spin and parity of nuclei with in ground state, all right. So, spin parity of nuclei in ground state. So, spin, when I say spin of a nucleus, what do I mean? This is total angular momentum. Remember, this is a terminology used in nuclear physics, not in atomic physics. In atomic physics, by spin we understand spin angular momentum, but in nuclear physics, if I say spin of this nucleus, it is the total angular momentum, not the spin angular momentum. So, that is the terminology used. So, when I say spin, it is J, total J, all orbital spin, everything combined for the whole nucleus, this is the final J. And then parity pi, whether the space part of the wave function is symmetric or antisymmetric, and this pi depends on L. So, if L is even, we say that parity is positive. Your space part of wave function will depend on this L, and if L is odd, we say that parity is odd. We had discussed little bit of this while doing deuterons, parity negative. So, as a superscript, it is written plus or minus. If it is written plus, that means parity is positive. If it is written minus, parity is negative, and J is the total spin. So, first even nuclei. When I write even nuclei, what do I mean? Huh? Yes, Z is even and N is even. Z is even and also N is even. These are called even nuclei. Now, one assumption or consistent with the observation is that in a particular energy level where you have 2 neutrons and 2 protons going, one with spin up, one with spin down, because all these levels which are drawn here. So, each will contain 2. So, quantum number n, quantum number L, quantum number j and mj, right. So, that is the, so those 2 neutrons or 2 protons in that same level, they will pair up, and pair up means if these 2 neutrons, for example, p half, in p half you have 2 neutrons, or s half you have 2 neutrons or 2 protons, or p 3 half you have 4 quantum states there, then 2 will pair up and 2 will pair up, and when they pair up to angular momentum 0 and magnetic moment 0, everything 0. So, we call it extreme single particle model, where we say that all neutrons and protons wherever possible they will pair up. Pairing decreases the total energy. So, it is some kind of an addition to this potential. This potential tells that okay, this is the energy, this is the energy, this is the energy. On top of that, we say that if neutrons, 2 neutrons pair up, Pair up means if they combine their angular momentum to 0 of these two, 0, J is 0 and Mj is anyway 0, those two only, not of the whole nucleus, then we say that they have paired up, and this pairing takes the energy down. So, as many pairs you can form, the energy of the nucleus is going down. So, in extreme, what we call extreme single particle model, we say that neutrons and protons will pair up to the extent possible, greatest extent possible, right. So, if you have even nucleus, all the protons will pair up and all the neutrons will pair up. So, if all the neutrons have paired up, all the protons have paired up, then the total angular momentum of the nucleus is also 0, because pairwise it is 0. So, 0 plus 0 plus 0 plus 0 plus 0. So, the whole thing is 0, it should be 0. So, spin should be 0, and since there are two of them, so whether it is L equal to even or L equal to odd, for each of the two, the parity will become positive. If they are in say d phi by 2 state, so d for this neutron, d for this neutron, so plus parity, combined parity is also plus. If they are on p 3 by 2, p L is equal to 1, but then so negative parity. So, negative parity of the first particle, negative parity of the second particle, total antisymmetric and antisymmetric multiplied become symmetric. So, parity is positive. So, independent of what levels these pairs are occupying, pairwise the parity is positive. So, the entire nucleus that also will have positive parity 0 plus. All even nuclei in their ground state, remember, will have
J is total angular momentum, but
J is, yeah,
but it is called spin of nucleus. Why it is called spin?
that is a terminology, okay. That is the terminology you must remember. The word nuclear spin is meant for total angular momentum of the nucleus. So, that is the term definition of that term nuclear spin. Right. Why that nomenclature has come, that could be some historical reasons, but today we only know that yes, if a nuclear physicist is talking of nuclear spin, he must have talked about the total angular momentum, right. So, all even nuclei in ground state should have 0 plus spin parity according to the extreme single particle shell model, and this comes out to be true in all experiments. So, that was about even. Now, next come to what we call odd A. Odd A nuclei, either Z is odd together with N even, or N is odd together with Z even. So, one is even, one is odd. So, the total will be odd. And what are the third variety possible? If even, then you had odd, and the other possibility is odd, both are odd. The total is even, both are odd. But very few odd nuclei, stable nuclei exist, right, some 4 of them in the lighter ones. Nitrogen 7 14, nitrogen 14 7 that is a stable element, and so on. So, deuteron itself 1 oxygen is 8 protons, it is not odd. Oxygen means 8 protons. You can have different isotopes, 16 oxygen, 17 oxygen, 15 oxygen, but that 8 you cannot change that 8. Oxygen is always Z equal to 8. So, Z is even. Okay. So, odd A, if you discuss even and odd A, you have discussed almost all the nuclei barring some 4 or 5. In odd A, now here that word that I used, extreme single particle, that is relevant here, because odd A means there is one neutron or one proton which does not have a chance for pairing. The total number is odd, and for pair you need 2. So, if there are 9 of them, only 8 can pair up, that 9th one has no chance of pairing up. So, in the extreme single particle model, we assume that the property of this nucleus is decided by that last nucleon only. Everything other which have paired up will give you 0, 0 spin, 0 parity, 0 angular momentum, everything 0, 0 magnetic moment. Only that last unpaired nucleon will decide all those properties. So, that is extreme single particle model. To some extent, even this simplified model works, and that we will see. Now, tell me some light odd A nucleus, and we will look at the spin parity of that. So, give me one, anyone. Nitrogen, odd A, okay, 7, you have to give 7 here, and then you can give 8 here, or you can give odd A. So, 6 you can give 6, or you can give 8, or you can give 10, 15. This will be odd A nucleus. Is it stable? Do not remember, I also do not remember, but let us work on it. If this is the nucleus for whatever time it is there, what would be the spin and parity in its own ground state? So, let us draw those energy levels. So, tell me what is the lowest one? 1s half. Next one 3 by 2. Next one
1 by 2.
Next one
1D 5 by 2.
1d.
5 by 2.
Next
2s half.
next.
1D 3 by 2.
All right, this is enough. 2 parts I have done, one for proton, one for neutron. Okay. So, 8 protons, 8 neutrons here. These 8 neutrons will go here. Right, lowest energy of the nucleus. 7 protons, where should they go? 4 here, P 3 by 2. 4 here. So, 2 plus 4 6 and 2 8. So, 8 neutron are going here, and then 7 protons. So, 2 here, 4 here and 1 here. All right. According to our model, this gives you 0 spin 0 parity, this gives you 0 spin 0 parity, this gives you 0 spin and 0 parity 2 pairs, and similarly this, similarly this. So, the spin of the nucleus is same as the angular momentum of this part, and that is half, J equal to half. So, its capital J should be half in ground state, capital J should be half, and since it is P state, L is equal to 1. So, the parity negative, right. That is how we calculate. Take another example, oxygen 15, same thing. Oxygen 15, what do you expect? Tell me. Spin parity. Neutron and proton different. Now protons 8. So, all these you will have a proton here, and you will have a 1 neutron here. So, same half minus, right. What about 17 oxygen? 8 protons, 2 plus 4, 6 plus 2, 8 protons will be there. Now 9 neutrons. So 8 neutrons and the 9th neutron must go here. So 5 by 2 plus, correct. It should be 5 by 2 plus. The ground state spin parity should be 5 by 2 plus. 13 carbon. Carbon is Z equal to what? So N is equal to 7. Okay. So Z is equal to 6. So 4 plus 6, correct? 6 here. And this one is 7. So 1 neutron will go here, correct? 2 plus 4 plus 1, 7, right? 7 neutrons and 6 protons. So what should be the spin parity? Half negative, yes. That is how you can calculate. And in most of the cases it comes out to be correct, right? Most of the cases it comes out to be correct. You can take for example 27 silicon. What is Z for silicon? Silicon is a very important element. 14, 13, right? So 14, what 14? Z 14. 2 plus 4 6 plus 2 8 and 6 14. And 13. So that means what should be spin parity?
5 by 2 plus.
5 by 2 plus, correct. So it is 5 by 2 plus. So most of these odd A nuclei you will find that this extreme single particle model prediction is correct. But I give you one exception also, and that is nickel 61. For nickel Z is 28, iron, cobalt, nickel. Iron is Z is equal to 26, then 27 and 28. So nickel is 28. So how much remains? How much remains? 33. Total is 61, correct? So now let us work it out. Let me draw the fresh diagram. Yeah, dictate me 1s half. Tell me. 1p 3 by 2. 1p half. 1d 5 by 2. 2s half. 1d 3 by 2.
And slightly above 1f 7 by 2.
1f 7 by 2.
2p 3 by 2.
Next is
2p 3 by 2.
2p 3 by 2.
And 1f 5 by 2.
Okay, that is enough. 28 will come up to here, right? So this is which side I take proton, which side neutron. Let us take this side neutron and this side proton. So 28 up to here, this will be 28, remember? 20 and this makes it 28. So everything up to here is filled, proton. Everything this, all this is filled, that will make it 28. And similarly 28 means okay, all 3, how do I write? 8 of them. 8 of them. Let me write 8p. All 8 protons are here, all 4 protons are here, all 2 protons are here, all 6 protons are here. That will make it 28, correct? Up to here it is 28. So up to here it is 28 neutrons. How many more are there? So 1, 2, 3, 4, 5. Huh? Ah, okay, okay. It cannot contain fifth. So n here. right. So, this the ground state should be, according to this calculation, J pi should be 5/2 minus. Now, the observed value is 3/2 minus. Observed value is 3/2 minus. Ground state spin parity of 61 nickel is measured to be 3/2 minus. No, is okay. So, that will be here, at since you have 61 these nucleons, therefore, the order will change, I told you, but that was here. Okay, that was here, not here. This order remains the same. How can I get this 3/2 minus as the ground state? Can you see a 3/2 minus in this scheme, where an odd neutron should be there in this scheme to give you 3/2 minus? 2p 3/2. You have 4 neutrons here. If you have 5 neutrons here, it will give you 3/2 minus, but 5 neutrons cannot come. This is 3/2 only. If not 5 neutron, 3 neutrons will also give you 3/2 minus. So, if this neutron is not here and this neutron is here and you have only 3 of them, that can give you 3/2 minus. But why should it go to a higher energy when the lower energy is available? And the answer is that if it is here, it will pair with this neutron. If it is here, it will pair with this neutron. Now, when 2 neutrons or 2 protons pair up, energy of the nucleus goes down, but by how much amount? It is not fixed, it depends on L. It depends on L. So, if 2 neutrons are getting paired up in p level, the pairing energy will be different. If they pair up in f level, the pairing energy will be different, and that pairing energy, the amount by which the total energy of nucleus is reduced due to pairing, is larger if the pairing is made in larger L state. Okay. So, it so turns out that if the pair is made here, the energy comes down by a larger amount than if the pair is made here. Here this is F, L is larger, here it is P, L is smaller, L is 1 here, L is 3 here. So, if pairing is done in a higher L level, that pairing energy is larger. So, it so happens that difference in pairing energy compensates, more than compensates for this rise, right. Here the energy is, because of pairing, energy is reduced by a certain amount, here it is reduced by a much larger amount. So, even if it has to go to a higher energy level, that saving due to pairing is more than this going up, and hence in ground state it is n here and n here. Right. So, that extreme single particle model is okay, is still working. We are only basis on that, only we can also explain this type of situation, nickel 61 type of situation, by taking proper care of pairing energy. Okay.
So, why we call only ground state?
We discussed ground state. Excited state also you can discuss with this extreme single particle model. For example, I give you the excited state of let us say oxygen 17. Oxygen 17, your ground state, I am telling you the observed values, 5/2 plus, then the next one is half plus, this is the first excited state, and the next one is half minus, and then you have phi by 2 minus and so on. Okay. Now, look at this 17O structure, you have 8 protons and 9 neutrons. So, protons will anyway form a closed shell, you have 1s half, then you have 1p 3 by 2, 1p half, what is next?
1d 5 by 2,
1d 5 by 2,
2s half,
2s half,
1d 3 by 2,
1d 3 by 2, enough. Protons we do not have to see, look at the neutrons only. So, you have all these will be filled, up to here it is 8, right. So, you will have protons and then protons and then protons. So, protons is anyway filled, neutron, talk of neutrons, alright, protons is also okay. So, neutrons up to here are all filled, and the next one is here, phi by 2 plus is okay, ground state. Now, if energy has to go up, this neutron should go here. So, the first excited state will be obtained if this neutron goes here, and if this neutron goes here, it should be half plus, and it is half plus. Next one is half minus. How can I get this second excited state half minus? Next one is 3 by 2. If this neutron from here it goes here, it should be 3 by 2 plus. It is not, it is half minus. The same story. This can give you half minus. So, if this neutron, one of these neutron goes here and pairs up, then you will get 1 by 2 minus. So, that is the second excited state, right. This pair is broken and here the pair is made. This is P, this is D. So, some energy is saved, but this energy difference is larger. So, it has gone up. So, even excited states also, many of the excited states also you can understand on this. So, we discussed ground state first, and then excited states also. Many of the excited states of these, at least these light nuclei, can also be understood using single particle shell model. Okay. Right. So, the next property that we will discuss with this model is magnetic moment of the nucleus.